Today's topic is electric field. So what is electric field? The magnitude of the electric field intensity at a point in space is defined as the force per unit charge that would be experienced by any test charge placed at a point. Means, suppose that a point charge is there, due to another point charge, if the force acting is F, then F divided by the charge carried, that is equal to electric field. So this is the formula, learn this formula, E is equal to force upon charge. What is the unit of electric field? Newton per Coulomb. The direction of E at a point is same as the direction that a positive charge would move if placed at that point. Means the direction of electric field will be considered the direction of the motion of the positive charge. Now see, the electric field at a distance from a single charge. Means suppose that we have to find out the electric field of this charge at this point P, which is at a distance of R. So how to calculate? Consider a test charge plus Q placed at point P. We have brought a test charge plus Q here at a distance R from capital Q. This is the charge capital Q. The outward force on plus Q. By the Coulomb's law, the force will be K capital Q small q upon R square. Now, from the formula of electric field, E is equal to F upon Q. So, F is this divided by Q. Q and Q cancel. So, what would be left? E is equal to K Q upon R square, or E is equal to 1 upon 4 pi epsilon naught Q upon R square. So, this is the formula of electric field due to a point charge. Due to a point charge at a distance R. Let's see the direction of electric field. Electric field lines first of all we have to discuss. Due to the positive charge, the electric field lines emerge outward, and due to negative charge, electric field lines comes towards the charge. So electric field lines are imaginary lines drawn in such a way that their direction at any point is the same as the direction of field at that point. So you may write a question, draw the electric field lines due to a single isolated positive charge and single isolated negative charge. So these are the two diagrams for such question. So next topic, we will see the direction of electric field and the motion of positive charge and negative charge. Suppose that this is a positive charge. If we keep a positive charge here to it, then it will move in the direction of electric field. But negative charge will move towards the charge, means opposite direction of electric field. Similarly, if the electric field is due to the negative charge, then how the positive and negative charge will behave in that electric field? Suppose that we bring a positive charge near a negative charge. Then this positive charge will travel in this direction, means in the direction of electric field, and negative charge will move away from the negative charge, means opposite direction of electric field. So keep reminding one thing, positive charge always travels in the direction of electric field and negative charge travels in opposite direction of electric field. The electric field lines, suppose that in first diagram, there are two charges, one is positive, another is negative. In second diagram, both are positive. So, you may write a question, draw the electric field lines due to an electric dipole. This is called electric dipole, we will discuss later. And due to two similar positive charge or negative charge. So, first see the dipole, the electric field due to an electric dipole. This is the diagram. Electric field lines emerge out from the positive charge and terminate at negative charge. This is the diagram of electric field lines due to a dipole. Draw this. It is very important. Now, suppose that you have to draw the electric field lines due to two similar charges of equal magnitude. If it is positive, then the arrow will be outward because electric field moves away from the positive charge. But if it is negative, then the arrow will be towards the charge, means the direction of arrow will be inversed. to draw the electric field lines. These are three diagrams. Mainly this may be asked in your ISC board or CBSC board paper, but these are competitive level question. So let's see first the electric field lines due to equal and opposite charge kept at a short distance, or electric field lines due to an electric dipole. So we have discussed this part. So you have to draw this diagram and write the question. Draw the electric field lines due to an electric dipole. Both are equal charges, plus Q and minus Q. Now this diagram. The electric field lines due to two unequal charges of opposite nature. One is plus 2Q and second is minus Q. So the charge of higher magnitude will have the denser electric field near it, and the charge of lower magnetic field, the charge of lower magnitude will have the lesser number of electric field lines around it. In third diagram, it is the electric field lines due to two equal and similar charge. We have discussed this part. Now see the next thing. This is actually the vector form of Coulomb force and electric field. Suppose that we have discussed this part, the vector form of Coulomb's law, vector x is equal to 1 upon 4 pi epsilon naught q naught upon r square r cap. Either you have to write this is the vector form, or second is this. Vector f is equal to 1 upon 4 pi epsilon naught q naught upon r cube vector. If you are putting vector sign over r, then you have to put r cube. If you are putting a cap over r, then you have to put r square. Now the vector form of electric field, we know very well electric field is equal to force upon charge. So E is equal to F upon Q naught. So E is equal to, vector E is equal to 1 upon 4 pi epsilon naught Q upon R cube or vector R. And E is equal to 1 upon 4 pi epsilon naught Q upon R square and R cap. Now these are the two graphs. In this is a charge and this is another charge Q naught. We have to find out the electric field and electric force over this charge. This is the coordinate Px, Y, Z. This is the distance. So this is the Coulombian force in vector form. This is the electric field in vector form. Now electric field decreases as we move away from the charge. So this is the graph of electric field versus distance. Now properties of electric field lines. So properties of electric field lines, there are 2 or 3 properties are very important you have to learn. First, I am just going to read, then I will mark the properties which are very important for the paper that you have to learn first. First property, the electric lines of force are imaginary lines. Second, a unit positive charge placed in the electric field tends to follow the path along the field line if it is free to do so. We have discussed this. The electric lines of force emanate from the positive charge and terminate on the negative charge. Learn this property. Means electric field lines originate from the positive charge and terminate at negative charge. Fourth point, the tangent to an electric field lines at any point gives the direction of electric field at that point. This is the electric field lines. If we draw the tangent, so this is the direction of electric field at this point. If we are drawing the tangent here, the direction of electric field will be this. Important, these 2 points are important. Then 2 electric lines of force can never cross each other or intersect each other. Very important, a question has been asked in the board paper. 2 electric lines of force can never cross each other. If they do, then at the point of intersection there will be 2 tangent. It means there are 2 values of the electric field at the point, which is not possible. Suppose that we are considering that 2 electric field lines can intersect. If they are doing so, then at the point of intersection 2 tangent can be drawn, which will show the 2 direction of electric field, which is not possible. Learn these points. Point number 3, 4 and 5. Very important points. Next topic is electric dipole. What is electric dipole? An electric dipole is a pair of equal and opposite charge separated by a very short distance. Suppose that this is minus q, this is plus q. Equal and opposite charge placed at a short distance, that is 2L. Then this system is known as electric dipole. So what is an electric dipole? Write this. The electric field produced by the electric dipole is known as dipole field. Means the field created by this system is called dipole field. Now what is electric dipole moment? Important. Electric dipole moment is a vector quantity used to measure the strength of an electric dipole. Means if you want to find out the strength of electric dipole, so you have to calculate electric dipole moment. So what is the formula of electric dipole moment? Electric dipole moment is equal to the product of either of charge into the distance between them. Any charge, whether you are putting this or this, but without sign you have to put q into the distance between them, that is 2L. So vector p is equal to q into 2L, or 2QL is electric dipole moment. The magnitude of electric dipole moment is the product of magnitude of either of charge and the distance between the two charges. The direction is from negative to positive charge. Means what is the direction of electric dipole? Important. It is always from negative to positive. What is the unit of electric dipole moment? It is Coulomb meter. Next, very important topic. It is a proving of this chapter. Electric field intensity due to an electric dipole. Very important. Write a question. Obtain the expression of electric field intensity due to an electric dipole. First of all, we will understand the diagram. This is an electric dipole, minus q plus q. This is the midpoint. The total distance between them, that is 2L. So from the midpoint, this distance is L, this distance is L. Let's from the center, there is a point P at a distance x, at which we have to find out the net electric field due to the electric dipole. So this diagram, you have to draw this diagram properly. Let's see the proving. At a point on the axial line, it is the electric field intensity at axial point. Resultant electric field intensity at the point P is. So net electric field we have to consider. First of all, we have to see the electric field due to the charge Q placed at B. This is EB, the electric field due to this charge outward. At EA, the electric field due to the charge minus Q at A in this direction. Both electric field are opposite in direction. So net electric field EP is equal to EB minus EA. So vector EP is equal to vector EA plus vector EB. The vector EA and vector EB are collinear and opposite. So EP is equal to mod of vector EB minus mod of vector EA. EB will be bigger than EA because this charge is nearer to the point P. Now, what is the value of EA from the formula? EA is equal to 1 upon 4 pi epsilon naught Q upon the distance of this charge from this point. This is x minus L. So what is this distance called? X minus, we have to discuss EA. So EA is this. So electric field at this point due to this charge will be x plus L. So EA is equal to 1 upon 4 pi epsilon naught Q upon x plus L whole square. Delete this I cap, it is not important for you, and do not put this vector sign here. EB is equal to 1 upon 4 pi epsilon naught Q upon x minus L square. EB due to this charge, so this distance will be x minus L. So that is 1 upon 4 pi epsilon naught Q upon x minus L whole square. Now the net electric field EP is equal to 1 upon 4 pi epsilon naught, in both of the equation is common, take out. Now because EB is this, which is bigger, so EB Q upon x minus L whole square minus Q upon x plus L whole square. On solving, we will get 1 upon 4 pi epsilon naught x minus L square x plus L square. When you will take the LCM, it will become x square minus L square whole square. It is A minus B and A plus B. So it is A square minus B square. Having the square, so it will become x square minus L square whole square. Now when you will open it, in the numerator you will get 2 bracket Q into 2L into X. 2QL is electric dipole moment, that is P. So in this, E is equal to 1 upon 4 pi epsilon naught 2px. P is electric dipole moment upon x square minus L square. So now if the dipole is very small, then L is very less than x, so L square can be neglected. So x square n square, that will be x ki power 4. X ki power 4 and x, so it will left x cube. So final equation is approximately EP is equal to 2p upon 4 pi epsilon naught x cube. The direction of electric field intensity at a point on the axial line due to a dipole is always along the direction of the dipole moment. Means the electric field is always in the direction of electric dipole moment. Let's see another proving of this chapter. That is, obtain the expression of electric field intensity at a point due to an electric dipole at equatorial position or broadside on position. So this is an electric dipole, this is the midpoint, the total distance is 2L, so from it L and L. Let from the midpoint a point Q is there at which we have to find out the electric field due to the electric dipole. This distance is Y. Positive charge will apply an electric field in this direction and negative charge will apply an electric field in this direction. Let's see this diagram separately. The EB can be resolved in two vectors, EB sin theta and EB cos theta. Similarly, EA can be resolved into vector EA sin theta and EA cos theta. EB sin theta and EA sin theta will be equal and opposite, will neglect each other. So net electric field EQ will be the sum of EB cos theta and EA cos theta. Now see, resultant electric field intensity at a point Q is EQ is equal to EA plus EB. What is EA? 1 upon 4 pi epsilon naught Q upon y square plus L square. Now, how the y square and L square? This distance you have to calculate. This is L, this is y. So this is Pythagoras. Apply the Pythagoras. So this distance will be equal to under root y square plus L square. Because in the electric field we keep r square. So r is equal to under root y square plus L square. So root will cancel from the square. So final equation EA is equal to 1 upon 4 pi epsilon naught Q upon y square plus L square. Leave this I cap. Similarly, EB is equal to 1 upon 4 pi epsilon naught Q upon y square plus L square. See, EA is equal to EB. So right here, EA is equal to EB. It is very essential. Now, the vector EA sin theta and EB sin theta are opposite to each other and hence cancel out. Means these two forces will cancel out. Now, the resultant electric field due to this and this. Now, the vector EA cos theta and EB cos theta are acting along the same direction and hence add up. So, net electric field EA cos theta plus EB cos theta, that is equal to EQ is equal to, because both are equal, so you may write 2 EA cos theta or 2 upon 4 pi epsilon naught Q upon y square plus L square. Now, what is cos theta? From this diagram, it is theta, so this is theta. Cos theta is equal to base upon hypotenuse, base is L and hypotenuse will be under root y square plus L square, so that is y square plus L square raised to power 1 by 2. Its power is 1, its power is 1 by 2. Now, it will become EQ is equal to 1 upon 4 pi epsilon naught 2QL upon y square plus L square, 1 plus 1 by 2, that is equal to 3 by 2. Now, EQ is equal to 1 upon 4 pi epsilon naught P upon y square plus L square raised to power 3 by 2. Then EQ is equal to 1 upon 4 pi epsilon naught, instead of 2QL we can put P upon y square plus L square raised to power 3 by 2. Leave this I cap. If L is very less than y, then we will neglect L square. So y square raised to power 3 by 2. 2 and 2 cancel, so y cube. So net electric field due to an electric dipole at broadside on position, that is EQ is equal to P upon 4 pi epsilon naught y cube. Now, the direction of electric field intensity at a point on the equatorial line due to a dipole is parallel and opposite to the direction of dipole moment. Proving, and very important, 2 or 3 marks question may be asked from this. Torque on an electric dipole in a uniform electric field. First of all, we have to understand this diagram. These lines are the field lines, electric field lines. This is a dipole, making an angle theta with the electric field. This is positive charge, this is negative charge. The positive charge will experience a force in the direction of electric field, F is equal to QE, and negative charge will experience the equal charge but in opposite direction of electric field, that is QE. So these two charges will experience two equal and opposite forces. So they will create a torque. So we have to find out this torque. So what is the definition of torque? Torque is equal to the product of force, either of force and the perpendicular distance between the line of action. So what is the line of action between these two forces? This line. We have to calculate this line. This is theta. This is hypotenuse. This is perpendicular. So sine theta is equal to perpendicular upon hypotenuse. So perpendicular is equal to hypotenuse into sine theta. So the value of this distance will be equal to 2L sine theta. Now see. Torque. Torque is equal to electric force into perpendicular distance. So torque tau is equal to QE. QE is the force and perpendicular distance, that was 2L sine theta. In the diagram mentioned 2L sine theta here. So tau is equal to QE 2L sine theta. 2QL is equal to P E sine theta. So this is the torque P E sine theta. Learn this formula. The vector equation, that vector tau is equal to vector P into vector E. Direction of torque is perpendicular and into the plane of containing vector P and vector. What is the unit of torque? That is Newton meter. These are the special cases when this torque be minimum, maximum and zero. So case 1, if theta is 0, means if theta is 0, then the torque will be 0, because sine 0 is equal to 0, so torque will be 0. Case 2, if theta is 90, means that dipole is kept perpendicular, then the torque tau is equal to P, which is the maximum value. Case 3, if theta is equal to 180, then tau will be 0. So what is the difference? In theta is equal to 0, torque is 0. In theta is equal to 180, tau is 0. This is the condition of parallel, and this is called anti-parallel condition. When the dipole is kept like this, it is the parallel condition, theta is 0. When the dipole is kept like this, means positive charge is this side and negative charge is in this direction, then it is called anti-parallel condition. So whether the dipole is kept parallel or anti-parallel, the resultant torque will be 0. Proving, and very important, 2 or 3 marks question may be asked from this. Torque on an electric dipole in a uniform electric field. First of all, we have to understand this diagram. These lines are the field lines, electric field lines. This is the dipole kept making an angle theta with the electric field. This is positive charge, this is negative charge. The positive charge will experience a force in the direction of electric field, F is equal to QE, and negative charge will experience the equal charge but in opposite direction of electric field, that is QE. So these two charges will experience two equal and opposite forces. So they will create a torque. So we have to find out this torque. So what is the definition of torque? Torque is equal to the product of force, either of force and the perpendicular distance between the line of action. So what is the line of action between these two forces? This line. We have to calculate this line. This is theta. This is hypotenuse. This is perpendicular. So sine theta is equal to perpendicular upon hypotenuse. So perpendicular is equal to hypotenuse into sine theta. So the value of this distance will be equal to 2L sine theta. Now see. Torque. Torque is equal to electric force into perpendicular distance. So torque tau is equal to QE. QE is the force and perpendicular distance, that was 2L sine theta. In the diagram mentioned 2L sine theta here. So tau is equal to QE 2L sine theta. 2QL is equal to P E sine theta. So this is the torque P E sine theta. Learn this formula. The vector equation, that vector tau is equal to vector P into vector E. Direction of torque is perpendicular and into the plane of containing vector P and vector. What is the unit of torque? That is Newton meter. These are the special cases when this torque be minimum, maximum and 0. So case 1, if theta is 0, means if theta is 0, then the torque will be 0, because sine 0 is equal to 0, so torque will be 0. Case 2, if theta is 90, means that dipole is kept perpendicular, then the torque tau is equal to P, which is the maximum value. Case 3, if theta is equal to 180, then tau will be 0. So what is the difference? In theta is equal to 0, torque is 0. In theta is equal to 180, tau is 0. This is the condition of parallel, and this is called anti-parallel condition. When the dipole is kept like this, it is the parallel condition, theta is 0. When the dipole is kept like this, means positive charge is this side and negative charge is in this direction, then it is called anti-parallel condition. So whether the dipole is kept parallel or anti-parallel, then resultant torque will be 0.